Okay, g'day viewers. Now, I've been watching a lot of YouTube maths videos over the years, and I've noticed there are some mathematicians that do go through various mathematical proofs, and I'd like the focus of my YouTubes to be the solutions to various theorems, in other words, proofs of mathematical theorems, which I believe is not taught in a lot of schools, and I think it's pretty important. And there's one in particular. It's the arithmetic mean, geometric mean inequality, which I haven't found that anywhere in the YouTube world. So I'm going to prove the general case of the arithmetic mean, geometric mean inequality. So here we go. Okay, so first of all, we're going to start off with a group of numbers, A1, A2, A3, all the way to AN, right? Now, all of these, A1, A2, A3 to AN, are going to be positive real numbers. Positive real numbers. Because we're looking at geometric mean and arithmetic mean, and, well, in all the cases that I've looked at, they're always positive. So, from there, we're going to introduce a function in order to help us derive this proof. That, and the proof, let me write it over here. We're going to prove that the arithmetic mean is greater than or equal to the geometric mean. AM is greater than or equal to GM in the general case. All right. So we're going to start with a particular function. We'll call this function f of x equals e to the x minus 1 minus x. Okay, now, again, these are all, this is for all x greater than 0. Now, sorry, that's not quite right. This is for all x. Sometimes written like this, for every x. Now, what you'll find is, for this particular function, if you were to draw this function, if you were to sketch it, or use some sort of graphing software like Desmos, you will find that f of x is always greater than or equal to 0. Always greater than or equal to 0. No matter what value of x you'll put in there, you will always get a value that's, for f of x, that's greater than or equal to 0. Okay. Now we all know that the arithmetic mean, and we'll call it alpha, is equal to the sum of A1 plus A2 plus A3 all the way to AN, which are these terms that we have up the top here, divided by the number of terms n. So we know that. That's the definition of the arithmetic mean. So what we're going to introduce is another term. We'll call it xi. Now xi goes from x1, it'll be x2, x3, all the way to xn. And in other words, we have I will be equal to we'll go from 1 to n. And this particular term, xi, is going to equal ai divided by alpha, where ai is just all our terms for the arithmetic, for the terms that we're going to use for the arithmetic mean, all the way to an. Right? Now we can do this because you see x can be any value for this particular function. So we're going to use this xi and we're going to incorporate it in this particular function. And we can do that because x can be any value. It doesn't matter whether it's any real number. So, and we know that ai is any positive real number, a1, a2, a3, a4. And we know that alpha is, again, it has to be some sort of positive real number. So this is what we're going to introduce right here. This is very important. So if we know that f of x is greater than or equal to 0, then we can create a new equation, and that equation will be e to the x minus 1 to the power of x minus 1 is greater than or equal to x. And we'll just call that equation 1. So because we know that f of x is greater than or equal to 0, we're just substituting that in there, and we're getting e to the power of x minus 1 is greater than or equal to x. So now we're going to use this and we're going to substitute all our different values of xi, which is x1, x2 to xn, and we're going to create a number of equations. So we have e x1 minus 1 is greater than or equal to x1. So what I'm doing here, I'm substituting the variable x with all the different terms for xi. So the first term will be x1, so I'm going to substitute that in there. The next one will be x2, and so on, greater than or equal to x3. And that continues on to e to the power of xn minus 1 is greater than or equal to xn. All right, but we know that xi is equal to ai over alpha. So in other words, so that means that x1 is going to be a1 over alpha. So we'll rewrite this now, substituting all of that in. So we have another group of equations over here. So this will be e to the a1 over alpha minus 1 is greater than or equal to a1 over alpha, because we're just substituting all the different terms of xi, x1, x2, x3, and we know that xi is equal to ai over alpha, and here are all our a values. So we've got a bunch of new equations. Sorry, that's a2 minus 1 greater than or equal to a2 over alpha. And then we have e to the a3 over alpha minus 1 is a3 over alpha, all the way to e to the an over alpha minus 1 greater than or equal to an over alpha. Now, we're going to use a, now of course there are n terms from beginning to end, right? That's important to realize that there are actually n of these equations, or I should say n equations rather than n terms. So there's n equations of the inequality equations. So we're going to use a particular little tool where if A is greater than B, or let's say A is greater than or equal to B, and C is greater than or equal to D, then you can show that AC is greater than or equal to BD. And you can do this for multiple terms. So that's what we're going to do. We're going to multiply all of these on the left with all of these on the right. And what we're going to get is E to the A1 plus A2 plus A3 all the way to AN all over alpha. So when I multiply all of these exponentials, I add all the exponents. So this is what I'm doing here. A1 over alpha plus A2 over alpha plus A3 over alpha. But of course then we've got all the negative ones there as well. And there are n of those because there are n equations. So therefore that's going to give us minus n. So this is our total exponent for E. And that is greater than or equal to. Now we multiply all of this together. And our top line will be A1, A2, A3, all the way to AN. So these are all multiplied, these denominators. We then multiply these are all the numerators. We now multiply all the denominators and they're all alpha and there's n of those. So we're going to have alpha to the power of n. So now we have this particular equation here. So the thing is, if you look at this part carefully, you'll see that that's just a rearrangement of the arithmetic mean. And that becomes e to the n minus n is greater than or equal to A1, A2, A3, all the way to AN, all over alpha to the n. So, well, e to the n minus n is just e to the 0, and that just becomes e to the 0 just becomes 1, right? So we can get rid of this now. We can change it to 1. And then what we'll do is we'll multiply both sides by alpha to the n. So the alpha to the n is going to come over to the left-hand side, right? So we're multiplying both sides by alpha to the n. So we now have alpha to the power of n is greater than or equal to this product. And from there, we take the nth root of both sides. So what we'll do is we'll take the nth root of the left-hand side, the nth root of the left-hand side, and the nth root of the right-hand side. This then becomes alpha to the power n is greater than or equal to the nth root of A1, A2, A3, all the way to AN. And this is the definition of the geometric mean. That should be alpha. And what I should have said was that this right-hand side is the definition of the geometric mean. And the left-hand side is, we know, is the arithmetic mean, alpha, as we brought in right at the beginning. So we have the arithmetic mean alpha is greater than or equal to the geometric mean, which is exactly what we're trying to prove in the general case. Thanks for watching.